Okay, so welcome to mobile communication now in the summer 2016, the course that basically sits on top of our telematics course. So you should be aware of the classical mechanisms in telematics. So what does multiplexing mean? What is TCP/IP? What is the basic networking for the fixed networks? So where we need all these wires and fibers and all these things. You should be aware and know basic protocols, TCP and IP, how they work, how DNS works, how backbones operate, what a router is, etc. Because now I will give you basically the add-ons to these systems. So I expect that you know how IP works, and then I will explain to you, oh, what are the problems with the classical IP? That means you have to know the classical IP. I will also talk about, for example, TCP, but you have to be aware of the classical mechanisms of a TCP to understand why TCP, the classical TCP, has a problem in the wireless domain. Okay, so, and anything else, well, look into the slides and you will understand. So it's not complicated, but again, like in telematics, many acronyms, many different systems, and by the way, one of the most complex systems at all. So, why do we do mobile communications? If you look at mobile communication systems, well, it's easy to see that this is really the largest software, hardware, network system with billions of participants. So the subscriber numbers in humans, well, 4, 5 billion subscribers, 6 billion, 7 billion, and even more due to all the machines, machine-to-machine communication. So billions of subscribers using these systems. Hundreds of operators worldwide. A hardware and software system that has to be compatible, backward compatible, but also compatible between the different operators, hardware vendors, etc. So that's complicated. And then if you look at the internet, all the mobile devices, they really dominate the internet. If you count the fixed systems, like the normal PC, like normal routers, servers, etc., they are by far outnumbered by the mobile devices. Just look at whatever, an airplane with 300-400 passengers with all the mobile devices, plus the mobile router on board of the aircraft, plus the 5,000 to 6,000 computers on board of an aircraft, all mobile. And you have to handle some things in a different way if you start communicating with these things. Then think of the Internet of Things just coming up. Industry 4.0, cyber-physical systems. So that means that due to the integration with more and more devices somewhere in our environment, and they start to communicate. Not everything is really mobile communication. If you look at near-field communication, for example, NFC, we used to open doors. Well, that's not really mobile communication, it's wireless. It's wireless communication. Yes, it's wireless, ultra-short range, maybe 3-4 centimeters. It's wireless, but not really mobile communication. But if you think of the airplane I mentioned, well, even if the systems are wired on board, the whole system is mobile and you have to handle this mobility somehow. So we have a lot of mobile applications, and if people talk nowadays about apps, they usually think of mobile apps or apps for mobile devices, apps for smartphones. And by the way, where's the big difference between smartphones and whatever, phablet, tablet, or the device here? It's a kind of a notebook, tablet, detachable. So there's no real clear border, as we had some years ago. We said, okay, this is a PC with the classical PC software, and a classical Linux or whatever, and now we have, these are the Android devices. Now you have Android on fixed device, you can run whatever links on this and that device, even on embedded systems. And then we have these bizarre devices, a little bit old-fashioned, ruggedized devices. Oh, waterproof, why do we need this? Well, go to a firefighter and give him whatever iPhone, and he should use it minus 20 degrees, so during fire, well, the device will not survive. No smartphone survives the use by firefighters in real scenarios. So you need different devices, different scenarios, different settings, and this is pretty challenging. I tell you this because we have several projects together with disaster recovery teams using mobile communication systems, and that's really more challenging. If the environment around you is something like 600 to 800 degrees, fire, smoke, water, etc. Okay, so interesting. We all know that we have many new possibilities. We all like these devices, we use them more or less, but we are also all aware, there are new threats. Many different threats. Yeah, you can lose your device. Well, okay, you can crack the screen, but the real threat is you cannot really control communication anymore. With the classical old devices, well, at least you could pull the plug and that's it. With wired communication, with wireless, how do you actually switch off a mobile phone? For most of the devices, you cannot even remove the battery. This one you can, but for many devices, you cannot remove the battery. Even removing the battery, how do you know that you removed all the batteries in there? Then if it comes to software, can you trust your operating system? Even if you trust your operating system, how many, or what do you guess, how many operating systems do you have in your mobile phone? 5, 6, 7, 8? Well, several. Even your little memory adapter or SD card, whatever, has a small little tiny operating system. Your SIM has an operating system. Your baseband modem has an operating system. Well, then there's the operating system like iOS or Android or whatever, Windows Mobile. But there are many other operating systems. And even if you really have a nice firewall around your Android or whatever, the operating system of your baseband modem can easily access your memory directly without asking the operating system, Android, whatever, and all the protection mechanisms. So that's quite interesting, and that's usually the way how you can enter a mobile phone. You do not ask the operating system, you go directly to the memory. So, okay, complete new threats because people do not understand how many of these poles we know you see at the airports where you can recharge your mobile phone. Really stupid idea. I mean, you plug your mobile phone with a USB cable to an unknown USB port. Do you know the software behind the port? You assume this is a power adapter. You assume you can charge, yes, you can charge your phone. But what happens in the meantime? It takes 10 to 15 seconds maximum to have complete control over your mobile phone. Any mobile phone, if you have direct physical access. Okay, there are nice devices you can buy, several thousand euros with adapters for all mobile phones. It takes some seconds and you can dump everything that's in the memory. Okay, so you should rethink before connecting your device to whatever system, so you don't know. But for wireless, yes, there are some more protection mechanisms, but you don't know, you don't see it, you don't know what's really going on. So, yes, there are some new threats and we should at least be aware of them. And what is the big difference also to a classical PC? This technology is now really integrated in your life 24/7. Yes, you have to recharge them, but usually the mobile phone, the smartphone, is the first thing you use in the morning and the last thing you use in the evening. Like, oh, is there something new going on whatever system you use, whatever software you use, etc. So, and now with all these fitness tracking systems, it's even stranger. Okay, so that's why we have to talk about the technologies behind. I cannot go into all the details of all the systems, but at least tell you the systems behind, the structure, the ideas behind, and then we can easily discuss many of the problems, issues, possibilities, etc. And by the way, this is also typical for this lecture. I rather skip some issues for good discussion. So please interrupt, discuss, ask. So I remember last year we had a lot of discussions about security, espionage, and this and that, and all these things that are interesting in the mobile and wireless world. No problem. So it's no problem at all. So if you have any questions, just ask. I don't know everything, but at least a lot about mobile communication. Okay, because we also develop those devices ourselves to learn a lot, etc., etc. So, mobile communication influences really whole societies. Even in countries where you think, oh, don't they have other problems? yes, mobile communications help them with many problems. For example, in Africa, M-Pesa is one of the most famous payment systems. Many of people there, they don't have a bank account. They will never get a bank account. Maybe there's not even a bank in the small rural village they live in, but many of them have mobile phones. So you can easily transfer money via the mobile phone. And if you go in the market there in Kenya, for example, you see someone, selling cucumbers or whatever, and has displayed the mobile phone number. So you simply transfer money from your mobile phone using the mobile phone number, and the one selling you cucumber sees, okay, I got my 30 cent, and gives you the cucumber. Very simple system called M-Pesa, and it works. So this is also the way grandchildren transfer money to their grandmother, grandfather on the countryside. So it helps a lot. Okay, so during the lecture, I will always give these types of examples. It helps you to remember the technology. But I also go through the classical layers. So after some introduction, some challenges, can go a little bit faster there. I will introduce exactly the frequencies. What I showed you in the spectrum analyzer, this heavy device here. I will tell you about cognitive radios, software-defined radios. What is MIMO? What are these new technologies? So why can we now transfer gigabits per second over the air? 10 years ago, maybe megabit per second. So why now gigabits per second? So what is the reason? How can we do this? We'll talk about medium access because this is now really a big problem. We do not have the wires anymore. So collision avoidance technologies. And after that, we basically have the technologies, we know the basic technologies to start the discussions of the real systems. Then first of all, I will cover the classical so-called telecommunication systems, starting with the second generation GSM, the most famous mobile communication system, going through the different generations until we end up at the fourth generation LTE, offering now megabits per second going towards the gigabit per second. So these are the large-scale systems. And then we go to the, smaller scale system, wireless LANs. Wireless LAN technologies, typically privately operated by companies, covering only smaller areas like our campus here. But just for comparison, to cover our campus, we need one antenna for these wireless telecommunication systems, but we have 1,850 antennas for the wireless LAN system. The antenna you see also here in the room, 1,850. So that clearly shows you, oh, there must be a difference. Yes, there's also a difference in data rate, in capacity, etc., etc. And now if you think of whole cities that want to cover the city with wireless LAN, and if you think that we only for our campus need 1,850, you see the relation. It's a problem. So you can never ever cover a whole city or a whole country with wireless LAN technology. It doesn't work, simply doesn't work. So you can forget it, or you get really mediocre data rates. That's something different. Okay, different technology. What is the difference? Then I will also talk about how can Bluetooth live side by side with these wireless LAN technologies, the 802.11, AB, etc., AC, N, so many substandards. And then we'll also briefly look into, okay, this is all the wireless technologies. What happens with the internet? The internet should be more or less technology agnostic. So we don't care what's down there, layer 2 and lower layers. So we have IP, we don't care. But as you will see, there are some issues. There are some issues if you do not know, do I have a DNS? Where's the server? What is my address? I don't have an address. I don't know the topology. How do I do routing if I don't know the topology? Or if I have a highly flexible topology, how does it work? So you suddenly see, the classical system, autonomous system, border routers, interior gateway, exterior gateway protocols, etc. They don't work anymore. So this is something we'll discuss also in the context then Internet of Things, etc. Also a little bit transport protocols. And then I will give a brief outlook to what's coming up of fifth generation. So Tokyo wants to start 2020 with 5G systems, and it will be interesting to see what happens there. So basically 5G has some very ambitious goals. So we want to enter really gigabit per second for all the end users, the latency down to milliseconds. Well, we will see if this is really achievable, but few milliseconds latency, etc., etc. Very ambitious, using many more antennas all over the place. Antennas with small transmit power to increase the overall capacity, as we will see. Okay, so that's roughly what we will cover during the lecture. Okay, so first chapter, a little bit more of motivation, but that's not too difficult to understand. There's a lot of motivation, a little bit of history and why this is interesting for us. So, how do computers look like? This question came up already early 80s. What are the computers for the next decades? And already there in the 80s, it was clear that sooner or later computers will disappear. There's a famous article by Mark Weiser who said, okay, the computers will completely disappear. And that's exactly what we see. We have a smart watch, which is actually a full computer. We have fitness trackers, we have smart walls, we have whatever gadgets, devices that are computers. We have mobile phones that are, yes, you can use them as a phone, but mainly these are computers that can do everything. Much smaller, much cheaper, portable, replaceable. Maybe not any more separate devices. Your fridge, your car, the car of the future. Yes, 4 wheels, and maybe the car drives from A to B, but mainly it's an IT platform. It's a platform where you can sell services. So that's quite interesting. And if you look at the computers, most of the computers are integrated. You don't see them. More than 95% in your washing machine, in your car, in whatever. The technology is not that important anymore. Like you had on a classical PC, which was a device, and you saw, this is the PC, and I have to take care of everything and plug in this and plug in that. And now the computers are more and more aware of their environment. So the computer knows where the computer is, how to react. So the smartphone knows exactly where you are. The smartphone knows the context. So the smartphones today, they can easily detect, now it's quiet, now I'm in a lecture. Why? Well, the smartphone has direct access to your calendar, knows the location, knows the surrounding, knows the other smartphones. So the computer is aware of the environment and can easily adapt. So location awareness is something new. So the computer can react appropriately. Well known is also call forwarding, message forwarding, no matter where you are. Well, you're used to all these things, you don't even think of it. But just think for a second of your mobile phone when you're in whatever country on this world. How does it work? How does the system know I'm there and now forwarding a message to you, forwarding a call, etc. So we will see how this works. We have a lot of advances in technology. Just think of the computing power we have today in these devices. It's really a lot. New displays. So I think we have more or less now reached the end of the pixel size in the displays, because with these displays you have today, you don't see the pixels anymore, and then, okay, that's it, that's the end. Because why should we have higher resolutions if we cannot see it anymore? But okay, we need new user interfaces. Think of the smart watches, or think of whatever. We are back to pens. Because a pen is much easier to handle compared to a keyboard. If you want to annotate something, you read something, you annotate, it's much simpler with a pen. So new user interfaces. User interfaces, you also saw in the last years that all the big companies came up with assistant systems like Siri, like Cortana, like whatever, that support you. And all these systems, they basically know everything about you. They know even more than you know about you, because they know what you will do in future, where you will go, they know your schedule, they know your behavior. They can also easily give you statistics based on the behavior of other persons, what will happen to you next, etc., etc. So frightening, but also a lot of opportunities. Interesting. We have a lot of advances in more bandwidth per cubic meter. What does it mean? Well, this is the space we have to use for wireless communication. Okay, and all the wireless devices have to use this space. There is no parallel space like we have in wires. So if this wire is not sufficient, we use an extra wire. We cannot use an extra space. So unless we find a way to go into a parallel universe and use this, but at least today with our transceivers we cannot use it. So we have to use this universe. Sure, okay, but there's a certain limit in bits per second, per hertz, per, the space you use. As we will see, you can use space division multiplexing, etc., but there are certain limits. And we have many, many new wireless interfaces. Near-field communication, door openers, for example, the new ID cards we have, Bluetooth, piconets, wireless LANs, wide area networks. We have many regional networks that cover rural areas where you do not have the DSL connection. It's much, much simpler to set up a microwave link compared to, well, using cable, digging in the ground, etc., etc. So it's much simpler, but you have some disadvantages as well. And we have something that is old and new at the same time, visible light communications, VLC, used since, I don't know, 4,000 years, something like this. So using some science and whatever. And nowadays we can transmit terabits per second using light. The nice thing there is you can easily integrate this into the LED light bulbs you use today. So because you can modulate the LED and you can simply transfer data. And this is now the experiments done, for example, supermarkets, which transmit over their light some information. For example, price changes to the little price tags you see at some goods, and you can easily then transfer the new price to the tag. The tag receives it. So that's something useful. Because you really get nice high data rates in peak, but you can also easily protect your device. Simply put it into a pocket. That's a big difference to lower frequencies. It's more difficult to protect your device when you use lower frequencies like 2.4 gigahertz, for example. Then you need some shielding, etc. So it will be interesting to see what's coming up. We will see during the lecture there are different aspects. I already mentioned, well, users are mobile. Okay. And users want to use the service more or less anytime, anywhere, no matter where they are. We want to communicate with anyone. Not that simple. Yes, you know the fixed internet, you know a lot of methods, technologies there, how you can find devices, but these are all fixed devices. Now suddenly we have mobile devices. So how does it work in terms of internet? I know this is my IP address, this is my network. Now suddenly I move from this to that subnetwork. How does someone find me? Not that easy. So portable devices, portable users, but mobile users. So it will be interesting. And there are many different use cases. So if you're wireless and mobile, that's exactly what we want with our smartphone. But there are also reasons where you have where you reconnect your notebook, maybe in a hotel to a faster connection, or at home, or if you have wireless LANs in historic buildings because you're not allowed to use wires. You're not allowed to drill holes, things like this. So it's quite interesting, many use scenarios, and as you can imagine, there are different organizations standardizing wireless and mobile systems. Most prominent is the standardization of IEEE in the local area networks, as you're used to with Ethernet, 802.3. We have the famous 802.11 for the wireless LAN. It's just an example, .15, Bluetooth, Zigbee and others. We have the internet. Well, there are, since I would say 20 years, 25 years, thoughts about how can we support mobility in the internet. Not really successful, to be honest. Standardized, yes. Used, not really. So, okay. multipath TCP used with Siri, etc. So there are some examples I will explain. And then there are wide area networks, the classical monopolistic telecommunication network, standardized by the classical huge organizations. And in this case, very successful. GSM, the most successful mobile communication system with, I think, more than 70% of the users worldwide use the original European GSM system. So very successful this. Voice over IP, classical old telephone systems, etc. So, and we have to integrate them. And this is a big challenge because you cannot simply say, okay, now everything is voice over IP over wireless LAN. No, we still have the old classical systems. We have the old telephone network. And now this year or next year, whatever, we'll completely replace the classical fixed connections you have at home with voice over IP. And something similar happens in the mobile systems. So with LTE, for example, we go to all IP networks and we leave the classical ISDN circuit switch networks we had with UMTS and GSM. So a lot to do also for standardization. Applications. Yeah, go through the slides. You will find many applications you're simply used to. Yes, sure, my mobile phone works also in a car. Works more or less also in trains, even in high-speed trains. Why? Why does it still work at 250 kilometers an hour? Okay, positioning via GPS. Why? How does it work? What can you do with it? Now, more and more, we will see these technologies also in the cars, for autonomous cars, for example, to prevent accidents. Because only with wireless technologies, you can see around the corner of a building. What happens there? So there are systems, for example, that automatically detect if an ambulance wants to cross your road, things like this. Why don't we have them in all the cars? Because this takes a long time. Plus, we don't know really who is responsible if something goes wrong. So if we have still a driver driving, we can always blame the driver. But if we have a pure computer-controlled system, who to blame? The algorithm, the computer, the hardware vendor, the vendor of the operating system, the manufacturer of the app. What happens if the first fully automized whatever car crashes into a tree or has to decide, now, okay, an accident is coming up, what should I do? If I go straight ahead, I will kill my driver or whatever, my car. If I turn left or what, I will kill the people on along the pedestrian area. So what should I do? Kill the people inside the car, kill the people outside the car. And that's one of the basic questions. How to decide? And that's an ethical question. That's very difficult. If you have humans, then afterwards you go to court and then whatever, you will discuss all the issues. If you have only computers, who to blame? Is it the app? Is it whatever, the software, the operating system? What happens if you have a virus on your car? Brakes don't work. The operating system of your car breaks down. What happens then? Do you blame the hardware manufacturer? Do you blame the operating system manufacturer? The app? Whatever, or a driver downloading this malicious app? Or someone exploiting this zero-day exploit or whatever? So very difficult. Okay, so yes, where do we use wireless communication? Sure, in all cases where you have a breakdown of the fixed infrastructure. The problem is, even for the wireless systems using a lot of the fixed infrastructure, like a mobile phone system, after an earthquake, everything is destroyed. Seconds after the earthquake, no more mobile phone system works, nothing. That's what we saw, for example, in Haiti. The only thing that worked is basically a wireless LAN that you set up after the earthquake. Then you can at least organize a little bit, which is not that easy because of many multiplexing issues, as we will see. So in all crises and all war scenarios, mobile communications, wireless communication is the only thing that survives, because the first thing everyone does is cutting the wire. For road traffic, yes, there is a typical example how many wireless systems you have today. You have all these wireless LANs already, for example, offered in trains, also in airplanes. So many airline carriers offer wireless LAN access in the aircraft, LTE, UMTS, but you also have digital radio, different technologies like Tetra, you're typically not familiar with, a system used by firefighters, so a trunk radio system, I will explain briefly. Inside the car, many different smartphone systems. You have NFC systems in your car, keyless entry, etc., with all the problems with keyless entries, Bluetooth systems, connecting or pairing, that's the term, pairing your device with the car. Also Bluetooth is used for pairing this pen with the laptop, etc. So many different technologies you use already today, and new technologies will show up. What we always want to have is something I call always best connected, ABC. A system that tries to connect as good as possible to some wireless networks. And if you see at the data rates, these are not the data rates in the commercials. You see, LTE up to 50 megabit per second. This is something you might get if you're happy. But just let's stay with LTE. If you look, for example, at the real data rates you get if you use LTE, just take a train from Berlin Central Station to Berlin Spandau, and you will notice, well, the LTE system breaks down 3, 4, 5 times in between, even in bigger cities. So there's still a lot to do. So while driving, etc., etc. So the real data rates you will get, they're a little bit less than the data rates that are usually announced. One of the reasons, it's a shared system, so it depends on the traffic. All the others course, yes, it's shared. Then it depends on things like the weather. The weather pretty much influences mobile phone systems. So in many countries, mobile phone systems, they break down during heavy showers. Why? Well, we have electromagnetic waves, and the rain absorbs the waves. What happens? Well, the rain heats up a little bit. That's the same effect you have in a microwave oven. Well, a little bit stronger waves, and this is your food, but in the end it's the same. Rain, electromagnetic waves, absorption, heating up the rain. That's it. You will not really notice it, but in the end, what should happen to the waves? Absorb. Also the trees. Now we have spring, that's worse conditions for mobile communications. Winter, better, no leaves. Because the leaves, depending on the size, are roughly have the size, the wavelength of the waves, so they operate like an antenna. Depending on the size of the antenna, they more or less absorb the energy. Oh, that's really a bad thing. Or after rain, you have water on the leaves. That influences. Or if the sun shines on roofs, then you have all the turbulence, etc., etc. So we will see wireless communication is not like wired, well, where all the waves more or less go along the line, and that's it. Okay. Many more applications, entertainment, etc., etc., etc. Many more services, not only applications, but complete new services. Location-aware services. That is something also the car manufacturers discover more and more. If you, for example, use one of the car-sharing cars here, you might have wondered, why do I get some announcement for some whatever special promo code for some of the supermarkets? Because the car knows where you are. It knows, oh, you're close by this and that supermarket. Then I give you this promo code where you get 5% off or whatever. So location-aware services. Because if you are on the road and you say, for example, you want to print something, you say print, it should be printed on the printer nearby and not somewhere here at the university when you're in the US, for example. All these follow-on services like call forwarding, that's something you're used to, no matter where you are. If someone dials the number of your mobile phone rings. There's a lot of forwarding of signaling information involved, because how does the system know where you are? By the way, does the mobile phone system really know where you are? As we will see, the normal mobile phone system doesn't know. So yes, your Google, Apple, Microsoft, they know more or less precisely where you are, but not the mobile phone systems. Okay, because at the time the system was standardized, this was too complex. So, okay. There are a lot of new information services, so push or pull service, so push services. So you see when you enter a supermarket, you could easily push new information on the devices. You know where the user is, and maybe there are some special offers. But you can also ask for where's the next ATM to withdraw some money, where's the next hotel, where's the next gas station, etc. A lot of support services needed. How do you cache intermediate results? How do you follow in the IT system a user to provide certain services? And as always, privacy issues. Who, for example, should gain some knowledge about your location? The technical system has to know something about your location. Yes, otherwise it doesn't work. I mean, you cannot find a mobile phone if you do not know where it is. Yes, so it's needed. The question is, how much of this information, how detailed should this information be when you want to inform whoever? Maybe the police, it should be very detailed for an emergency call. But for a mobile phone operator, maybe not that detailed, just enough that the operator can operate the network, etc., etc. So that's quite interesting, a lot of discussion. Maybe part of the discussion is also very special for Germany. For many other countries, no one cares. People easily give away all the information. But okay, that's up to everyone. The problem is most people do not know how much information they give away automatically. So, but you should be aware, and I will give you several examples, at least after this course, you should be aware that you give away, using a smartphone with all the features, you more or less give away all the information, everything. So even the smartphone knows how many steps you take, knows all these things. It's very simple to get this information from the devices. So you don't need the fitness tracker. Okay, many services. And if I talk about devices, I do not really care about, is it an embedded sensor somewhere in some machine? That's what we use for tracking endangered birds, for example. Or is it some kind of smartphone, some tablet, some whatever, with more or less performance? There is no clear separation. It was maybe 15 years ago, but today you cannot really say that is a PC, or that is this, or that is that. For example, now with the new Windows, you do not even distinguish while programming the devices anymore. So it's more or less one platform. The same happens to many other platforms. Still, yes, today you have Android and the classical Linux, but more or less you also see no borders anymore because the display size is more or less the same. The performance is more or less the same. Yes, we still have less memory, some problems in the interaction, but in the end, well, no big difference. Okay, so many different devices. We have some, however, effects of device portability. So one effect is the power consumption, and there we have the problem of that the power consumption is proportional to the capacity. Well, what does it mean? Basically, if you design a circuit, highly integrated circuit, you have all the transistors, you have the memory, and you always have, as you might have learned in some of the lectures, certain capacity in the transistors. So, and you load the capacitor, you unload it, etc. So it depends proportional to this capacity, proportional to the square, to the square of the voltage. So you reduce the voltage there, but also proportional to the clock frequency. So that means if you really want to achieve high performance, you need high parallelism. That means a lot of transistors, higher capacity, and higher frequencies, and that wastes energy. It really wastes it. Why? Well, not in the physical sense, but in the end, it heats up your device. That's exactly, notice, oh, the device becomes warmer and warmer and warmer, so it wastes your battery power. So that's a problem, and still this is the main limiting factor. If you think of smart watches, for example, you have to recharge after 1 day, something like this. Okay, maybe some people like it, I don't. So it depends. Smartphones compared to old classical mobile phones. Well, recharging classical mobile phones every 2 weeks, every 3 weeks. Smartphones every day, during the night, if you really use them. But yes, you can do a lot more. Watching movies, music, etc. So yes, there are some effects of the portability, then loss of data. That really is a big problem because, so the real physical loss of the device, more or less this device knows more or less everything about you. Where you are, what you have done, many passwords to accounts, mobile access to whatever, etc., etc. So this is really a big problem. So if you design services, you have to keep this in mind, that you might lose the device. And then it depends on the design, system design, how much information you actually store on the device, how much you have in the cloud, etc., etc., etc. The user interfaces are somewhat limited. Yes, smartphones you can use with one hand and your thumb somehow, depending on the size of the thumb. But there are some limits when it comes to the keyboard, etc., etc. So I guess in the future we will see devices where you simply speak to the device. You simply speak, and as you see with the Google Glass or the HoloLens and all these systems, you will see the result projected into your glasses, and that's it. So no more interaction with your fingers, because that's not the natural way for humans to interact with devices. Yes, okay, typewriter, we use this, we use the keyboards, but really since thousands of years we use voice, we use our eyes to see something, but not the fingers to type a text. So, okay. But we have still limited user interfaces, so we have to use different symbols, emojis, etc., all these things. And then we still have problems of limited fast memory. Yes, the mobile devices, I don't know, we have 64 up to 200 gigabyte SD cards now, 200 gigabyte for a mobile phone, plus integrated some gigabytes. So there's pretty much memory, but an SD card is by far not as fast as a RAM or SD RAM. So there are still factors in between. So we will see what the future will bring there. It's not the capacity, it's the amount of fast memory. So this is still some problem. But 200 gigabytes in your pocket, that's okay. So for some movies and whatever. Okay, so there are some effects we will also discuss. So when we compare, we're still in this overview with fixed networks, we will see, and this really caused some problems, we have much higher loss rates in our wireless systems due to interference. If you have a fiber optics, we have 10 to the minus 12 bit error rates, 10 to the minus 15. So, okay. Here, for wireless systems, well, 10 to the minus 2, 10 to the minus 3. So you flip every 100th or every 1000th bit. That's quite a lot. So we have more regulations. So you cannot simply say, oh, I love 4.5 gigahertz. That's nice. All my neighbors, they are all at 2.4 gigahertz. I use a system at 4 point something gigahertz. Depending on your output power, it will take only some minutes to some hours before someone rings at your door and asks you, what the hell are you doing there? So the government, also companies, they permanently monitor the air to avoid interference, because there are some frequencies used for air traffic control, radio astronomy. Some frequencies used for whatever military applications, for the police, for radio, TV, etc. So we'll see it's heavily regulated which frequencies you can use, and if you use certain frequency, in addition, certain regulations, output power, transmit time, etc., etc. Overall, the transmission rates are always lower in wireless systems. Yes, you might think of, oh, at home my DSL is only whatever 20 megabit per second, but LTE is 50 or 200, as the commercial says. Yes. The big difference is usually if you have a more or less stable DSL system and a good operator, you will get your 10 or 20 megabit per second, whatever is promised almost. There is some interference with neighbors, yes, because cabling, etc., as I told you in telematics. But with wireless systems, it's always up to, because, well, during peak times, you have many people trying to access the networks and the data rate really breaks down. With much higher delays, higher jitter. Why? Well, the problem is, depending on your connection quality, you have to put a lot of effort into forward error correction because of the high bit error rates. And forward error correction means you have to do some computation with your data. This introduces some delay. So you always have higher delays. You always have lower security because, as you saw, with such a simple device, I can easily eavesdrop into all the frequencies. No problem at all. And with software-defined radios, for some euros, you can build your own GSM base station. It's no problem. And as I will show you, not all of the systems are really protected. So much lower security, or maybe you've heard of the man-in-the-middle attacks for the keyless entry into cars. Yes, it operates only if you're close by your car. Yes, but if someone builds a relay between your car and you sitting somewhere in the cafe, it feels for your key as being close to your car, which you're not. But then you can easily open the car. Okay, so things like this, so much simpler to attack all the wireless systems because you don't need the wire. Yes, I told you can also attack wire system, but you always need some kind of physical access. You might notice or not. Then it's always a shared medium, always. So it's always medium. Yeah, we talk about medium, but in contrast to fixed systems, we don't need a real medium. Simple proof, even for kids, the sun is shining. There's vacuum in the universe. No one is out there. There's no cable between the sun and earth. There's nothing. Pure space is enough for the transmission of electromagnetic waves. When I say the sun is shining, that's nothing but the transmission of electromagnetic waves at several terahertz, which we call light, to the earth through vacuum. Nothing, nada. Well, we can now discuss if the quantum fluctuation is really nothing, etc. But that's a different issue, different department, physics. For us, it's nothing. So we don't need a medium like the air, because many people say we transmit over the air. Yes, but we don't need the air. So space, that's okay. Okay, so brief history, just to give you a little bit of context. Well, wireless communication is pretty old. Flags, waving flags, etc. That's wireless. Visible light communication with some bits per minute or whatever. Smoke signals, yes. So it's reported many years ago. What's quite interesting, the optical telegraph, a real telegraph system operating also across Germany, Berlin to Aachen, etc. with huge signals, and then we could actually watch to the other tower and a system of many towers. If you're interested in this, go into the Technical Museum, but if you enter it, the left-hand side, there's a very interesting exhibition about internet communication, etc. And they explain all the details also about optical communication, the history, with nice pictures, explanation, everything. So it's very, very nice. And, you can learn a lot there, and they have all the examples. So that's quite nice. Okay, if it's a rainy day, go there. It's quite interesting. So for us, it's important to have the electromagnetic waves. We can modulate, we can control. Yes, the old system of using light, okay, not really for our purpose for higher data rates. We had some theoretical foundation, but it was interesting. The first demonstration back in Karlsruhe, where Heinrich Hertz showed in the lecture hall, where I gave the first instance of this course, where he showed from one corner of the lecture hall to the other corner, I can really transmit something over the air. Electromagnetic waves. That was the first practical experiment where he showed, okay, it works. James Clerk Maxwell showed in theory there's something like electromagnetic fields, wave equations, etc. But many people at those times said, yes, we need something like an ether, we need something to transmit this. We don't, but first we needed the experiment. Then we had first telegraphy, fully digital, but the output power was quite high, more than 200 kilowatts. That's quite a lot compared to the milliwatts we have today. We had already more than 100 years ago commercial transatlantic connections with huge antennas, voice transmission 100 years ago. More or less exactly 100 years ago, first wireless voice transmission between New York and San Francisco. Before that, we had the cables and the telegraphs and Morse codes, etc., etc. But this was not really practical because these huge antennas we needed, due to the fact we could only generate long waves, low frequencies. Marconi discovered also short waves. Short waves means small antennas. Discovered that you can transmit these waves around the globe, and then the vacuum tube was invented that's needed for amplifying the signals, and there was already 1926 the first train phone between Hamburg and Berlin. That's quite interesting. So that was Marconi. With TV broadcast 100 years ago, almost 100 years ago, even color TV, then frequency modulation, I will explain some more details later on, was discovered. After World War II, there were several systems developed during the World War, but the first commercial civil use in Germany was the so-called A-nets. A-nets at 160 megahertz, pure analog, then B-nets, 1972, also analog, but you see the customers. Wow, 10,000, 13. Why? Well, huge devices, very expensive, so not that simple to use. And also you had to know roughly where your communication partner is to dial the right prefix for this area and all these things. So complicated. 82, or some time ago, there was the first idea of a pan-European specification of communication system, GSM. So 82, and the idea was also to have a digital mobile phone system. So 82 was more or less also the time the first personal computer started, where at least people could imagine that the size of computers shrink. Before that, we had huge computers, and so then people started thinking, oh, maybe 10, 20 years from now, computers could shrink. Okay, then, but still, well, the time was not there for a pure digital system. There was the C-nets in Germany, still analog voice, but digital signaling, and at least, well, 98% coverage, fax, modem services. We had the specification of the digital cordless telephone standard. So the cordless telecommunication standard still used today. That's for all the cordless phones operating, you see here, almost at 1900 megahertz. And a special feature there is that you can support many users per square kilometer. So more than 10,000 users per square kilometers. So that's a special feature. And then early 90s, GSM started. GSM really a success story. First time it was possible to use the same mobile phone in different European countries with, and today more than 200 countries. And you're all well used to this, natural. Then we had the enhancement, A-nets, we had the first standardization in wireless LAN technologies, wireless LAN with higher data rates, but it all started, you see, some megabit per second. And end of the 90s, well, we had the first specifications for the successors of GSM, because at that time it was already clear we need the support of more and more data service. That was the upcoming UMTS. And also the hype around satellites, global satellite service, like Globalstar, Iridium, etc. Then we had more and more standardization for wireless LANs, start of Bluetooth, you see, then decision about the new third generation standards, different standards there. GSM was upgraded to higher data rates, and 2001, the first 3G systems were available in Korea, the CDMA 2000 system. So I will present all these different systems and the basic ideas there later on. Okay, then after we had the problems with the internet economy at 2000, well, many bankrupt startups. It took some time, but then UMTA started, and we had more and more higher data rates. 2006, with 250 megabit per second for wireless LAN, with more than 3 billion subscribers for mobile phones. 2008 was more or less the year when we first had the real internet also on mobile phones, because we could use standard browsers and decent data rates, so some megabit per second. Then 2010 was the year when LTE, long-term evolution, started, and in some, I think Oslo, Stockholm were one of the first cities there. And then 2015, last year, the operators introduced voice over LTE, and that's more or less the step when you say goodbye to the classical transmission of voice, which is still in the classical LTE UMTS GSM system based on circuit switching. And with voice over LTE, we've also there a full voice over IP network, so an all IP system. And 2015 was also started to use LTE on different other frequencies. You heard that the old frequencies for analog television has been sold for LTE, etc., etc. Also for the old frequencies for DVB, the terrestrial digital television, will be used for other services, and this is why we will have DVB-T2 on different carriers. And 2020, it's planned to have the 5th generation 5G. This is what I will explain a little bit more in the outlook at the end of the whole lecture. So you see a lot of development in the last, I would say, 20 years. So 20 years ago, no one really imagined this tremendous success of all the devices. And it's funny to see that it's not always technologies. The iPhone is a good example. It's what we call plastic integration, because the technology in there is not really advanced, but it's the ecosystems of apps nicely adapted to the technology, so it makes you feel more or less comfortable to live in this world. It has a certain price tag, but it's comfortable, and this was the key to the success. It was not an advanced technology, it was not the fastest processor, it was not the best whatever. No, not at all. There were other devices with faster processors, whatever there is. But you see, history shows you even huge companies that completely dominated the mobile phone market, like Nokia, gone. Don't exist anymore. Now they sold the maps to the car manufacturer, and that's it. So it's interesting to see, but I guess most of you do not know Nokia, for just the example, is still extremely successful as a vendor of all the systems in the background for the infrastructure of mobile phone systems, and this is where you really make the money. The problem is with smartphones, only very few companies really make money. Even big companies like Samsung, etc. They have their problems because the pressure on the price tag is enormous there. This is why they always want to sell content in addition. Now, that's one of the problems. Okay, why is it interesting to participate in this lecture? Because it's important. This is an old prediction of 1998 here. What will happen to the mobile or wireless subscriber numbers? And the prediction was at 2000 we will have something almost 700 million. 2014 we have more than 7 billion subscriptions. So not people, but subscriptions. It's always a big difference how many active subscriptions we have. So old prediction, we look at also an old prediction about the so-called mobile phone penetration. The penetration at the turn of the millennium, almost, Finland was 60%, Germany was, well, not even 20%. 2005 was between 70 and 90. 2016, we have 96% worldwide. Worldwide, 96%. So, and in many countries we have 120 to 150%. Just count how many mobile phones you have, you owned, etc., etc. So interesting in cars, in etc. So, and if you look at the global developments in information and communication technology, we see here in this color, almost lighter blue, that's the fixed subscription, fixed broadband. At the same time, you see the upcoming mobile broadband subscription. So it took some years. It's now all, well, 3 times as many as the fixed subscriptions. So, and also the individuals using the internet increased. Mobile cellular telephone subscriptions. So, and this is always per 100 inhabitants. So this is this penetration figure. So you see, fixed networks are nice, but most of the people of this planet, they use the internet or whatever it is with their mobile phones. And this, by the way, was one of the headaches also companies like Facebook, etc. had and sometimes still have. They live pretty much on the advertisements. But if you have a small screen, plus you place advertisements, people don't really like this. But if more and more people only use the access to all the systems with their mobile device, or now imagine using their smartwatch, is there any space for advertisements left? That's a problem. So if you access all your messaging services only via your smart whatever device with complete different interfaces, there's no space for advertisements. So how do you make money? Big problem. Okay, there are some internet companies, they don't want to make money. So for example, Amazon, they never made money. So they're not interested in making money. So that's a different business model. They just want to grow, grow, grow. Okay. Cellular subscriptions, you see, which is quite interesting, is the increase also in the so-called developing countries. So the definition of this you will find using the URLs. If you see in the developing countries, the penetration, this again is the penetration. It's close to the world average, 90 to 95%. In the so-called developed countries, it's 120%. So this is why I say it's the tool for communication all over the world, not the fixed networks. Try to install fixed networks in countries where you have crisis. How? Very difficult. That's the first thing that's interrupted are fiber optics, copper wires. Very difficult. So, and you also find figures for the penetration, so mobile cellular subscription per 100 inhabitants in the CIS, that's the former Soviet Union, more or less, to be politically correct, Europe, Arab states, etc., etc. So you see extremely high rates. Also, when you look at the share, we had 2000 between the developing countries and the developed countries. So I said, okay, oh, that's a technology only for the rich developed countries. True 2000, not true anymore. As you see, 2014, developing versus developed countries. So that pretty much flipped. Yes, still, it's almost impossible to afford a full-featured smartphone for most of the people on this planet. Yes, way too expensive. This is why many companies, we even don't know the names, are pretty successful in some countries by offering cheap mobile phones, which use this, well, basically you can use them for placing a call, for accessing the internet, but you don't have all these features, not all the powerful processors, not the gaming support, not the 3D accelerators and whatever. You usually don't need as well, but okay. Different story. So, quite interesting. This. Okay, what has all this to do with the things we do? There is a lot of research still there. Although we have so many nice systems with high data rates and whatever, still we have problems in the wireless communication itself. So how can we increase the transmission quality? Decrease bit error rates. Decrease error rates. decrease the delay. Delay is one of the biggest problems. So how can we code many bits per second onto our signal, although we have interference and all these things? How can we organize medium access? Well, again, we have the problem, like we have in the classical internet, that all the systems have been designed for this bursty office traffic, accessing files, printing something, etc. And now suddenly you use it for, well, replacing your telephone. Voice communication over wireless systems, never designed for such a purpose. That's a problem. How can you prioritize this voice traffic? It's an IP packet. Difficult. Then mobility. Well, on one hand, we need location-dependent services, like where is the next this and that, show me this, show me my friends nearby, etc. On the other hand, we need location transparency. I want to access whatever, no matter where I am on this planet. I don't care. So transparency, but also dependency. We need a lot of quality of service support. So if you want to access a service with a certain quality, you need some support for this. But if you multiplex all different types of traffic, how can you support this quality? Open question. Then portability raises several issues like power consumption. Yes, that's a big problem. If you really use the devices with all their features, you drain the battery pretty fast, within a day, no problem at all. Limited computing power, display size, as I mentioned, if you have special gadgets, it's difficult. Usability, and then, as always, security issues. Privacy, how much of your private details you want to give away. What are the incentives for giving away all details? Just an example, if all the insurance companies gather all the data they can get about you, that's a big problem, because then insurance will not work anymore, because they can pretty much predict, plus minus, what diseases you will have, more or less how long you live, how dangerous it is for you to travel, to use a car, etc., just based on statistics. Now imagine someone really gathers all the information about you, knows exactly your behavior. Then insurance doesn't work anymore, because where's the risk? You can more or less predict what happens. Sure, there's always some statistical error, but not comparable to when you say, okay, I have insurance for more or less a whole population of a country. If you know exactly the behavior, this can be pretty dangerous for all these business models also for insurances. So this will be very interesting to see what happens there. So, interesting. Data integrity, what happens to your data? Do you want to give away? Can you avoid giving away the data? Sometimes there are situations where you want to give away. Sometimes you want to be tracked. Sometimes the system has to track you. Sometimes the system wants to track you, but you don't want the system to track you. Big issue. Encryption. The same thing. Yes, you can encrypt all your data. Okay, this raises the level a little bit for all the secret services. They have to enter your mobile phone and get the data directly at the source. Okay, but on the other hand, we want to have law enforcement. You want to have a look into the mobile phone of a terrorist. So, big issues there. Big issues, and especially with mobile devices, it's really, really difficult to decide how much information you want to give away, how much you have to give away, how much information is good for society, law enforcement, whatever, for commercial purposes, for etc., to give away. So that's quite interesting. Just imagine there are companies also here in Berlin, they sell a simple service. They tell shop owners how long do people stand in front of your shopping window. You don't have to know who is standing in front of the shopping window. So you change something and then you can ask, do people now wait a little bit longer and look at something? Because they simply know how long is a certain mobile phone at a certain location. It's exactly the same you use for traffic information. It's exactly the same for, well, if there's somewhere a fire in a subway, you can check only based on the wireless LAN beacon signals, mobile phones, you can basically count the numbers of people in the subway station, because you assume that more or less most of the people have mobile phones. So many interesting applications where more or less everyone will say, oh, that's something, yeah, that's a nice application. But with the same data, you can do many other things, because you know exactly where the devices are. So, okay, so these are the things we can discuss, and this is also pretty much where we are working on. It's one of our main focus is public safety and security with mobile communication systems. So that's what we work on. Okay, so, well, when we come to the lecture, we have to organize it somehow. That's the reference model, not a big surprise. The only new thing, well, not the only, but is, yes, we have a radio link here. And this radio link sure influences the physical layer, which I will discuss. Influences also a lot on the data link layer, and then also a little bit here on transport layer up to the applications. But most of the systems we'll discuss will come up with new methods for accessing a medium, for coding, and so on. So that's a simple reference model. You're used to this, no big deal. Then what do we have to look at? Physical layer, frequencies, that's what I showed you with the spectrum analyzer. Interference, wave propagation, all these things. Why do I explain this? You're studying computer science, not electrical engineering, yes, but you have to have a basic understanding of this so that you know why we have to do something in the higher layers. You have to have a basic understanding of the problems of wireless systems, not the details of wave propagation, not the details of all these formulas that are there. We do not look into formulas, but you have to understand the basic issues there. Also when it comes to the data link layer, because their medium access is different from fixed networks. I always told you in telematics, it's so boring with the star topology switch networks. No more collisions. Here we have one medium, only collisions all the time. So many collisions, many different ways of data that really creates collisions. Network layer, device location, addressing, routing, it's quite important. And so for mobile ad hoc networks, over the last 10-15 years, I think more than 500-600 routing algorithms came up. Because it's so difficult. We don't know how really to do it. Besides, yes, flooding. Okay, flooding you can always do. Okay, and some more issues when it comes to quality of service, etc. So in the end, the global goal we want to have is, today we have many of these systems, in-house wireless LANs, body area network, campus-wide wireless LANs, metropolitan networks. They all work. I will explain to you how the horizontal handover works. But what we also want to achieve is so-called vertical handover between the systems. And this only works in parts, so that you can, without service interruption, easily go out of this lecture room with your device connected to the wireless LAN and you using voice over IP in the middle of a teleconferencing session. You go out of the room and without service interruption, your whole service is handed over to a wide area network telecommunication system. Complete different operator, different networks, completely different. No service interruption. So this is a challenge. There are some systems, they support this. We'll come back to this. So, and this together with high service quality, etc., etc., is also one of the goals of the 5th generation of mobile phone systems, where you basically integrate all the different systems there are, like wireless LANs, like this telecommunication system, the wide area telecommunication systems. So that is basically still the global goal, that we integrate all these different systems. Okay, so that's more or less all for the introduction, and you know now roughly we'll talk about first these lower layers, give you some of the basics of physical layer, of wave propagation and all this you have to know to understand the problems there. We go into multiplexing technology. There's primarily code division multiplexing, something new, not known in the fixed networks. And then pretty soon we will enter the telecommunication system, GSM, the infrastructure there, because this is basically the blueprint for most of the new telecommunication systems. They basically copied the architecture of this tremendous successful GSM system and said, okay, now how can we implement new air interfaces, etc., etc. It's complex. I give you an overview. Just only the GSM system, more than, I don't know, 15,000 pages in standardization. 15,000 pages. That's pretty much. And that's quite difficult. But the nice thing is you can look into it. It's freely available. You can download it. Feel free. But it's quite a lot. Okay. That's it for today. If you have any questions, please interrupt. I hope you understood. You always feel free to interrupt, to ask, then we can discuss everything. And the next time, next Wednesday, I will then really start at the lowest layer, the physical layer. Okay, thanks a lot for today and see you next week.